So I think I mostly should not start a talk with a disclaimer, but I am a mechanical engineer, so this is actually not much of a coding talk. I don't show much code. It was supposed to be a Python users conference, so I wrote it saying how we use the code, and I thought it might be interesting. But the people who made this talk are not software engineers and not even physicists. We are just mechanical engineers who are trying to use this code. This is a talk about detector cooling systems. So we are a department that cools the silicon detectors inside in CMS and Atlas and also LHCb. And I thought I might start first with just giving an overview of what the cooling systems are like. So essentially, you have two common types of cooling systems: a vapor compression system, which you have on the left, which is what you have in your fridge in your house. So it's a compressor that goes into a condenser with hot gas. So you cool it down, you expand, and then you evaporate, and you have cold air available inside. Or you have a liquid cooling system, which is what you have in your car, for example, where you have a pump that goes with its liquid into the engine, picks up the heat, and then you can take the heat into the cabin of the car, or you can dump it out of the atmosphere, and then you can repeat these. These systems both are useful for what they do, but not so much for detectors, because a vapor compression system has oil, which you don't want in radiation zones, and a liquid cooling system has thermal gradients, which are also not wanted. So what we have used for the past 15 years or so is what is known as a two-phased pumped loop system, which essentially combines the best of these two worlds. So you still have a pump, so it's a small installation, but then you do two-phase evaporation, which is very, very, very thermal stable. And these things are useful for detectors because they are quite fragile, with silicon not wanting much thermal gradients. So these systems, as I said, have been used for a long time at CERN, starting actually first with an installation that was meant for the space station on the alpha magnetic spectrometer. So this was the first one that was designed, but due to delays in the launching, we actually ended up with the one on LHCb first. And since then, essentially every update that we have done to the detectors has been using more and more CO2 technology, which was all well and good. But most recently, we had this mandate for cooling all of CMS and Atlas in the high-lumi upgrade with CO2, and which means things really went order of magnitude or sometimes 2 orders of magnitude higher in flow rates, cooling powers, and so on. The sizes of the things also became bigger. What used to be a small skid, big like this, is now an entire room in CMS. So with all of these things, we had to do a lot of things new in how we design the systems and how we simulate the systems and so on. And in the past, like all good mechanical engineers, we were all using Matlab for everything. And we built up this huge sort of toolbox of pressure drop, heat transfer coefficients, and so on calculations, and for solving ODEs with all of the plotting and so on. But Matlab CERN would like to stop using it as much as possible. It's not open source, it's not free. And then also to go from NXCals or Timber, the database, to what we wanted to plot in Matlab was a bit more convoluted. So we said, why not take the chance to learn something new and start playing around with Python? So we've been slowly doing this over the last year or so. And this is just some small snippets of what we have done with it. So I divided it into three subcategories: the simulations, which let's say happens before we build the systems, the actual data analysis and commissioning of the systems, which happens with the system, and then some stuff on the visualizations of the system. So as an example, I show you simulating what is probably the most important component of what we use, which is called an accumulator. What it is kind of like a pressurizer in nuclear industry. It is a vessel that always holds two-phase CO2, so liquid at the bottom and vapor on the top. And you can control the pressure of it by heating or cooling the CO2 inside. And because it's two-phase, if you heat it, you sort of push the gas onto the liquid, and you make the pressure go up, which, because it's two-phase, pressure is directly correlated to temperature, so the temperature also goes up. And vice versa, if you cool it down, you can't see it because of this guy, but if you cool down the vapor, you condense the gas, and then therefore you lower the pressure. So we have to have good models of this because we rely on this to control the dynamics of the system. And before, we used to model it in a homogeneous manner, which means that the whole thing assumes a uniform property, a uniform density, only one enthalpy, only one internal energy, and so on. To make this two fluid model, we used Python, and actually first I show you the homogeneous model. This is kind of the Matlab implementation of it. It's extremely simple because it's just the construct that you see here is how you solve all differential equations in Matlab, where you basically have the two governing equations, the mass and the energy balance, and the derivatives of these state variables are in y, and your coefficients and so on are in a, and on the b you have the boundary conditions. So for the mass balance, the boundary is that the flow rate coming in minus the flow rate going out leads to a change in density inside the volume. And same with the energy going in and the energy going out, and plus the change of energy inside. All of this is conserved because of the second law of thermodynamics, or the first law of thermodynamics rather. And so this was the implementation in Matlab. We could solve it with the ODE 15S or 15I, both of which are variable step solvers for differential algebraic equations. For the two fluid model, we have the same similar equations implemented in Python, but here we had to use NumPy. But this model is also quite a bit more complicated. So here you don't just account for homogeneous property, but also the idea that if you suddenly increase or decrease the pressure, you create bubbles inside the volume of the accumulator, or you have suddenly condensation appearing that falls down as rainfall. So these kinds of effects are somewhat tricky to understand, and not much literature exists on this. So we wrote a model from scratch to play around with this, and could use some really nice solvers actually, which are better than what is available in Matlab in Python. Specifically, Radao is the one that Modelica, if any of you has heard of it, also uses, and this is quite a good one. Here I give an example of why we would need a model like this. So often we have a lot of fluid arriving, or you need to quickly change the temperature of the detector because maybe the detector requests that we must quickly go warm because of humidity concerns and stuff like this. And so here we did an example also in real life, but here I show the simulation of quickly going from cold to warm. And what you see is that this blue line shows you the liquid phase, and this red line shows you the vapor phase. And as you pressurize quickly, you actually start to subcool the liquid a bit, and you start to superheat the gas. So it's not a homogeneous model. They're actually not going together. They exist as different phases. And as you go up, you can pressurize them. And because there is now a delta T, a temperature difference between the two sides, after you reach the top, you see that the temperatures have to equalize, and the gas basically goes down to the temperature of the liquid. And therefore, you also see it in the pressure. So your pressure dynamic predictions are different than what they would be in a homogeneous model. This is a kind of toy example. It's not big dramatic consequences, but you can actually find issues where you can have pretty dramatic consequences of not modeling it properly. This white vessel that you see in the foreground is a 12,000 liter CO2 vessel that we recently installed on the surface. And this is where we will store all of our CO2 when it's not needed. And this is it cannot handle too high pressure, so we have to really be careful about keeping the pressure constant. And if we had modeled this using a homogeneous equilibrium model, which was from the Matlab case, if you assume that the flow coming from the underground was at this temperature and this mass flow rate, it's kind of a high mass flow rate. What you would find is that it would, because the flow coming in is cold, it's actually really cold, this everything mixes inside and is in homogeneous and in equilibrium. So actually you would see that your pressure actually drops because you're cooling down essentially what's coming in. And so you would be convinced that everything is going very well because you can easily regulate the pressure. You don't have to do any heating or cooling. The thing takes care of itself. But actually, if you model it with the two fluid model, as we did with the new code, what you see is actually the opposite happens. So the liquid is getting extremely subcooled here, but the gas is going warmer and warmer. And so the pressure is actually increasing. This distance, luckily for us, is not too big because there's not that much CO2 underground to make this a dramatic case. But actually, the conclusions are the exact opposite in the two cases. So it was actually a useful exercise for us to have made this model and to look at the different cases that we have. That was the simulation part of it, let's say before we actually have the real systems. Now a little bit about once we do have the real system and we want to start analyzing the data or post-processing. I give an example of scanning the pump. So when we have a new system arrive, what we want to do very quickly is to scan it and learn about the performance of it. It has different components like the pump, like heaters and so on. And what you want to be sure of is that the performance is not degrading over time. And so you need to take a baseline of the performance in the beginning. And one of the way we do it is by basically giving a little extra pressure head over time to the pump and seeing how the flow rate of the pump behaves. And what you typically see is that the pressure is quadratic with flow rate. So we would close this valve to give some pressure head to the pump, and then nothing would happen, nothing would happen, nothing would happen, and then all of the action happens right at the end. And this is not so nice for data analysis because you cannot take linear steps. You have to take smaller and smaller steps as you get closer to the end. So we had the brilliant idea of actually closing the valve itself in a quadratic or exponential way so that the pressure itself would be linear. And this was implemented using the equations that you see on the screen. After the implementation, we even had the idea of letting the system scan itself. So instead of a guy every half an hour clicking on the valve or reducing it by 10% and so on, we programmed the SCADA that it would reduce itself every 10% with time. But before we could figure out the implementation and if it would have any impacts on alarms triggering or safety issues and so on, we actually wrote some code to simulate the behavior of the real plant over time as we would do this scan. So initially, it quickly goes down linearly to find a minimum position, then goes back up, and you can see the parabolic decay of the valve. And on the blue line, you can see that the pressure is sort of taking steps. And overall, if you plot the trend of it, it's quite linear. We even added some fake noise to represent how the real pressures behave as you go higher in pressure, and you see a much more bouncy behavior from the pump. And then it goes down, and to avoid hysteresis problems, we also go up again with the same slope, and so you have going up and going down, so you can cancel out any hysteresis cases. Then it takes the next step, and it goes to the next temperature set point, and so on, and the scan continues. This way, we could quickly make changes to the code, show it to the PLC programming engineers, and get feedback from them if we were on the right track or not. And this is now having done the scan in real life. You see the results. So on the top, you see the full implementation. So this is the valve going down, up, and so on. And then this is the pressures, and then here you see the temperatures change, etc., etc. We had the data. We took one part of it, and then you can do your statistical analysis extremely easily with pandas. Actually, I was very happy to find because it allows you to take this CSV and just sort of reshape it however you want or move it back and forth and in a very easy way. And so here we were just basically trying to find the steady state points by looking for deviations in the standard or changes in the standard deviation. And anytime it was high enough, we took that as a trigger point for a change. And then between the trigger points, you can take the steady state values and then you can analyze it very easily. So you take something that is a dynamic data over many, many hours, and then you can just get a few points and then you can do whatever you want with that. This is the overall results of the pump scan. So many different temperatures, stroke length, speed of the pump, and so on. Okay, the last part of my talk is about some visualizations. So I've always had this problem of when you have a lot of data to analyze, you see it in graphs, and graphs are quite information dense, but they're not very easy to parse, at least for someone like me. So I had the idea of creating a kind of visualization tool for seeing these systems in real life. So what this is a heat pump system where you can do both heating and cooling in your house using the same system. So in the cooling case, the compressor sends it to the condenser where it's cooled down, expand, and then you have cold air inside your house. But you can also flip this valve such that the output of the compressor goes first into your house. So the hot from the compressor you can use inside your house to create heating, then send it back outside to do the cooling. So in the winters, you can use it for heating, and in the summers for cooling. And what is a plot like this on the right side of dynamics, you can actually get a much more visual understanding of how the system behaves, how much the length is inside the condenser that you're wasting, cooling and heating and so on, and what are the different flow rates in the system, the pressures and so on. This was all written over a fever dream in Matlab, and I had a lot of problems adding functionalities to this kind of code, because if I wanted to have multiple pH diagrams, for example, the pressure enthalpy diagram that you see on the bottom, there was no easy way. So at this a couple of weeks ago, actually, I sat down and decided to make it in Python a bit more properly. And here is a bit of a comparison between the two ways I did it. So in Python, I actually decided to make modular construction. So the data is only read by the data analysis module. The geometry of the components is handled by another module and so on. And then a YAML file to specify everything about your cycle. So how many components, connectors, and so on. And this is kind of nice because you can sit down and create the system first and then put the data inside it. So this is now the similar implementation in Python. This cycle I already showed before. This is early stuff, but it's the implementation in Python. But what I'm really pleased with is I could even get things like this. The lines actually show you where the valve position is. This sort of stuff is a bit more possible in Python to change the connectors and so on. And even the homogeneous and the two fluid models that I was showing you, we are also working on building a realistic implementation of them with the heater and the cooling coil and the accumulator and so on. So I have some of the repositories linked here if you would like to see them. It's all pretty broken stuff. I'm not really any good at structural thinking about software and so on. So if you can look through them and give us advice, I am very happy to take a look. One last slide just on how I found the transition between them. So MATLAB and Python are both not really particularly fast. I was using C++ when I was in high school, and then this was the fast way of doing things. But the thing about MATLAB is that every file can only have one function, or it can be a script. So you have to organize your code in folders, and you're always changing paths and so on. This is much nicer in MATLAB in Python because first of all, you have many more data types, which I mentioned in the next line, but also you can put an entire module in one file, which I found quite nice. Of course, in MATLAB, solving differential equations is nicer than it is in Python because you have the backslash operator. But on the other hand, pandas and so on, this does make afterwards the life easier. And then in MATLAB, everything is a matrix, even a 1D scalar. But in Python, you have much more rich or expressive types of to express different kinds of constructs. So this was just some reflections early into Python. Thanks a lot.